If you were going to sell food in a can, what kind of a can would you make? Would you make one that is tall and thin, or one that is short and wide, or somewhere in between? Well, you probably want to minimize the amount of material, the amount of metal you use for that can, for the same amount of volume. So what cylinders minimize the amount of material? Suppose we want to minimize the surface area of a cylinder of radius r and height h of fixed volume. The volume, pi r squared times h, the volume of a cylinder, that is a constant v. And now the area will be the area of the top and the bottom, twice pi r squared, plus the area of the side, that's 2 pi r times h, that is the area of this side. And since h can be expressed in terms of r, like this, we can plug in h into this formula and get a formula for the area that only depends on the radius. Now that we have a function of one variable r for the area, we have to minimize this function for values of r between 0 and infinity. When r is 0, this blows up and the area is infinite. And when r is infinite, then this is infinite, and therefore the area is also infinite. So we're going to find a minimum somewhere in between 0 and infinity. And in the interval, in the open interval from 0 to infinity, this is a continuous function, so the minimum will be at a local minimum, which we can tell by the zeros of the derivative. So we take derivatives. This is the first derivative, and we're looking for critical points, which are those that make this vanish. So we look for a 0 of the derivative, which means that 4 pi r equals 2v divided by r squared. And if we solve for r, we get that r cubed is v divided by 2 pi. Therefore, there is only one critical point for this function between 0 and infinity, and it happens at this value. And now we need to figure out if that's a local min or a local max. For that, we take the second derivative of the area function with respect to r, and we get this function, and then we see that it's positive at that value, so that is a local minimum. But in fact, all of these values are positive between 0 and infinity, and that means that the function is concave up, and therefore this is a global minimum at that point. Now that we know the value of r at the global minimum, we can figure out the value of h, because we have a formula for h in terms of r, and if I plug in r in that formula, I get the value of h at the global minimum and the value of r at the global minimum. And what matters of this relationship between the two is that this is actually twice that value. So this happens if and only if this happens, that h is twice the radius. So to minimize the surface area of a can, of a cylinder, all we need is that the height should be twice the radius. Well, it turns out that Eagle brand condensed milk is the winner.